And today we have one of the finest mathematicians on the continent. So in person of Professor Tony Ezome, and he's from the Masuku University. So Professor Tony Ezome has done a lot of work in the development of mathematics in Africa, to which I can testify to. So his area of research is in the algebraic geometry, number theory, and applications. So today he's going to be speaking on normal basis, Galois correspondence, and finite field arithmetic from algebraic groups. So Professor Tony, you're welcome. So you have 45 minutes or thereabout to speak. So you're welcome.
Thank you very much, Praise. Maybe I can add a few words concerning Marco Garuti. As Praise said, we met him during a summer school, which was co-organized by our network, which is Prima here. I think you see Prima, Pole of Research in Math and Application in Africa, and SIMPA, and also AIMS Cameroon in Limbe. It was the first time for me to meet Marco. And we passed 2 weeks, very interesting weeks, very intensive work. So I keep it in my mind, and this was very grateful. So just to say this word concerning Marco Garuti. So for the talk today, it concerns normal basis and how we can use it to do Galois theory and finite field arithmetic, and also using algebraic groups. Let's see the, it's strange. Yeah, it's okay. Let's see the context. So I recall what is a normal basis of a Galois extension of field. So we have capital K over small k, Galois extension of field. Usually I will consider only finite degree. What we call a normal basis is a basis generated by an element which I call theta, and the action of the Galois group of this element. And this is normal basis concern mathematicians since many, many years. The normal basis theorem, which gives us the assurance that we have always a normal basis for a finite Galois extension, was conjectured by Eisenstein in the 19th and proved by Ansel for finite field extension, and then by Noether for arbitrary finite Galois extension, and recently in 1985 by Lenstra for infinite Galois extension. As I said, normal bases are useful for Galois correspondence to release Galois correspondence constructively, and also for finite field arithmetic. So I start by the case of Galois correspondence. So this is the plan of the talk, as you can imagine, from the context. So I start by recalling the fundamental theorem of Galois theory. So we know that if we have a Galois extension, a finite Galois extension with Galois group J, then for any subgroup of the Galois group, we have a subfield, which I call also an intermediate field. And so, in fact, we have a bijection between the subgroup of the Galois group and the intermediate subfield of the Galois extension. We have the inverse of the map. And this map is inclusion reversing, and the index is equal to degrees. And if the Galois group, the subgroup is normal, then the corresponding intermediate field will be Galois over the base field, and we know the Galois group. We have also the infinite version. Now I'm going to explain how we can release constructively Galois correspondence by using normal basis. So as usual, we have a Galois extension, finite Galois extension, capital K over small k. We assume that we have a normal basis of this Galois extension. Now we want to release Galois correspondence. That means that we want to go from an intermediate field to get the corresponding subgroup, and on the other side, to go from the subgroup and get the corresponding intermediate field. So when we say that we have the Galois group, we mean that we have the matrices, sorry, representing all the automorphism in the Galois group with respect to the normal basis. Now, if you want to go from an intermediate field, we know that this intermediate field is separable over the base field, since the Galois extension, since the field extension, this field extension is Galois, so it is separable. All intermediate subfield will be separable. So from we have a primitive element. So, and we know from the primitive element theorem, we know that we have an element which generates the intermediate field. And then saying that we are given an intermediate field means that we have the expression as a linear combination of the primitive element in the normal basis. And then the corresponding subgroup of the Galois group will be the element in the Galois group which fix the primitive element. Now, if you want to go from the other side, this means that we have a subgroup and we want to compute the corresponding intermediate field. We know that this subgroup has an index. We call R the index. Then G is a partition of the right coset. And what we call Gauss period of the normal basis with respect to the subgroup will be this element, this summation. In fact, we have the partition, we have for each class a representative, and we consider the summation, the sum of the element in the action of H on an element in one representative of the right coset. And when I go in from 1 to R, we have all the Gauss period. This is Gauss period. Since N is a normal basis, and the fact that the right coset from a partition, we know that we see clearly that the zeta I are linearly independent. It is also easy to see that an element with this combination, linear combination, is fixed by the element in H if and only if it has constant coefficient on every right coset of H. This means that zeta I is in, for any I, zeta I is in the fixed field. And since the number of zeta I is equal to the degree, we conclude that we have the fixed field, which is this direct sum. And we can do more. In fact, the zeta I, the Gauss period, form a normal basis in the case when the subgroup, the original subgroup, is a normal subgroup of the Galois group. For example, this is the case when the Galois group is an abelian group. Okay, and here I use I give some example of Galois extension. The first one uses Kummer theory, in fact, we have what is important is to know what I will call the Kumar polynomial of this form. So I assume that the base field is a perfect field with characteristic P, positive characteristic. Consider n an integer, and I take a couple of elements, small a in small k and b in the algebraic closure, such that b is an nth root of a. And we also assume that k contains an n root, a primitive n root of unity, a primitive, I forgot here, primitive n root of unity, which means that this element generates all the primitive on the n root, all the n root of unity, the n root of unity. Then this extension is a Galois extension, is a cyclic extension with degree n, and such an extension is called a Kummer extension. Now let's go to Artin-Schreier theory. We do the same, but here the polynomial is this one, and when the polynomial is this one, we have what we call Artin-Schreier extension. What is important here is the fact that this polynomial, I will call it Artin-Schreier polynomial. Now, a few words concerning Affine varieties. We consider this for this part that small k is an algebraic field, and we know the affine and space over K, this set. We have on this set the Zariski topology, and we know that from the Hilbert-Husserl that closed subset corresponds to radical ideals. In particular, K rational point corresponds to maximal ideal. And what we call an affine variety is an algebraic, a closed subset for which corresponds to a prime ideal. And what we have, what we call an affine, the ring of a regular function, and we can use it to define the dimensional variety. It will be the transcendental degree of the Fiedler fraction of this ring of regular function. We define also, we recall what we call the smoothness of the variety, and here we have what we call morphism of variety. I see here K morphism to say that the component of the morphism have a coefficient in K. The product of variety is again a variety, but we have to make attention because the Zariski topology on the product is not usual. It's not usually equal to the product topology. There are many examples. For example, we can think about the line, the affine line, to understand what happens. And now we have what is an affine algebraic group over K. This is a topological space with a group structure given by this M, the law, the group law. And the inversion are rational, regular map. And what we call a morphism of variety is a morphism of a morphism of algebraic group is a morphism of affine variety, which is also a group homomorphism. And when the two groups are connected affine algebraic group, and the kernel of the morphism is finite, and the morphism is surjective, we say that we have an isogeny. In particular, if we have a connected algebraic group and H a normal subgroup of J, then we have on the quotient J over H, a structure of connected algebraic group. And we have an example of isogeny from G to the quotient. This is an algeny with degree. The degree is equal to the cardinality of the kernel, I mean the cardinality of the subgroup. And we have the classification. We have a classification of a affine algebraic group in dimension 1. We have the first one is the additive group, which is the affine line, and though with the x coordinates, we have the group structure is the sum of coordinates. We have also the multiplicative group, which is we can say in A1 or in A2 as you want, and we have a group structure. We have also the Lucas tori, so we have an element alpha. Here I mentioned that here the field K is only perfect field, not algebraic closed field. It is only a perfect field. And then for that, alpha is not a square. We consider alpha non-square. Then we define what we call the torus, and it is a variety given by this equation, and it is also a group. So it is an algebraic group. This is up to isomorphism. We have three affine algebraic group in dimension 1. We have also in dimension 1 projective algebraic group, which are elliptic curves. Here I recall what is elliptic curve. We are in the projective plane. Here I recall what is a plane curve. An elliptic curve is given by what we call a Weierstrass equation. That is the locus of this polynomial. And on this curve, we have a group structure, and it is a projective algebraic group. Actually, any projective algebraic group with dimension 1 is an elliptic curve. This means that we have, in fact, up to isomorphism, four algebraic groups. We have three affine and one, and not one, but one class of projective, because there are many elliptic curves. So divisor on the curve, it is a formal sum of points on the curve, and we have what we call principal divisor. This is the divisor coming from a function on the curve, and for principal divisor, the number of 0 is equal to the number of pole. I remember that I recall, sorry, that the 0 and the pole are the point which are involved in the divisor, in the principal divisor. And here I just the definition, and the degree of the function on a curve is equal to its number of 0 or number of pole, as you want. Here I give an example of function and divisor. We have this elliptic curve. We can see that we have two parts for the elliptic curve. We have the affine part and the point at infinity. There is only one, and this point is a unit element. And we have two functions, x and y. We have the degree. If we put 0 here, if we consider f equal to 0, we will get y squared equal to sx. And also, yes, there is also this one. There is the f3y. We have, if we put x equals 0 here, we have this equation, and this equation degree to have two solutions. So we have two zeros. Since a function has a number of 0 is equal to the number of pole for a principal divisor, and we know that on the affine part we have only zeros. This means that the point at infinity is a pole, and with order 2, with the same argument, we find that this is divisor of the function y. From this function, we consider the translation. We can do the translation on an elliptic curve because we have a group law. And using this notation, we have this function, and this function will help us to construct normal bases. We know that for our talk, normal bases will be used. We saw how to use them to release Galois correspondence. We will see also how to use them to do finite field arithmetic. So this function is very important. There is another example with the same argument. We have another equation. We go from the affine equation, and here we homogenize the equation. We have the projective closure. In fact, this equation is it is considered in the projective plane, but it is really in the projective line, because this point and this point are sent to 0 and the point at infinity. Then I mean that what I want to say is that the projective closure of the Lucas torus is the projective line. And so we have also a function which is interesting in this case. This is this function which is constructed by the function x and function y here from this equation. And we have its polar divisor. We know that this function has degree 2. So this means that we have two poles, and we can check easily that the point has the unit element, and this point T which generates the FQ rational point over the torus. Now, how to construct a Galois extension from algebraic group? What we have to do is to consider commutative algebraic group, how we saw. We know that we have this isogeny, and what is important to get to construct a Galois extension is the following. We just need a point in in H, a k rational point in H, such that the fiber of I above A is irreducible over K. If we have this condition, then the field obtained from small k by adjoining all the fiber is a cyclic extension of K with degree n. I choose to explain you a proof of this claim. We know that the component of the point in the fiber are in the algebraic closure, and all these are algebraic over K. So this field is an algebraic extension of small k. Since small k is a perfect field, this extension is separable. Moreover, the fiber is reducible. This means that it is normal. The extension is normal, then, and it is Galois. Now we want to see that the degree, it is cyclic, and the degree is equal to m. The first thing is that the kernel is given by the subgroup by which we factor the group. And we know that the kernel can be written like this. Since this is reducible over K, we can describe the Galois, the action of the Galois group on the point in the fiber. It is given by this. This helps us to see that the Galois action on B on the fiber helps us to see that in fact the Galois group is abelian, and it is abelian with exponent dividing n. Now we have to consider kappa, the non-generate pairing. It is a non-generate pairing. This is easy to see. This non-generate pairing gives us an isomorphism between the Galois group and this cyclic group. But the cyclic group has order n, then we can conclude that the Galois group is cyclic with degree n. Now, let's switch to arithmetic in finite field extension. So here we consider fq to the m over kfq. And we know that this is a Galois extension, Galois group generated by the probability automorphism. Then and theta generate the normal basis under the action of the Galois group. But since the Galois group is exponential by Q, we have this. And so what we can see that is that if we take an element like this, we want to compute the power to the Q. When we do this, this corresponds to a cyclic shift of the coordinate because of well-known rule by using the characteristic of the base field. So exponentiation by Q is easy, is cheap. Now, if we consider theta a basis which is not normal, we have, and we want to do arithmetic. If you do addition of point, of linear combination of point expressed as linear combination in theta I, it is easy. You have just to factorize. But if you want to do product, you will get product, good product, but you will also have this cross product. And what we call the complexity of theta, it is the minimum number of operations needed to compute the coordinate of the product of A and B in the basis. This means that we have to know this T sub I, G, and up. Okay. So we have a billion form, which come. And when the base, if the base theta is normal, this billion form, Sika, can be obtained by 1. In fact, they are related under the Galois action. They are related under the Galois action. And then we have a naive algorithm to compute the complexity of an arbitrary basis. So we first see that we have the weight of the basis. We call it small w. And we know that to know what we want to compute is the coordinate of this product in the base theta. This means that we want to compute this billion form. And for 1 billion form, we have this product, which means that we have each term is 2 products. Each term is 2 products. How many terms do we have? We have omega term because omega is the number of non-zero. And how many additions do we have? When we have omega term, we have omega minus 1 addition. This gives us a complexity, for a naive algorithm. But there are other methods to compute for computing the complexity. In the following, we use the Karatsuba algorithm. It is a well-known algorithm. We want to do the product of 2 polynomials. To do this, we do our usual the product, but we can see that there are at least 2 methods, the naive method, which need to compute this product, and this one, and do addition. But we know that usually to compute a multiplication, a product is expensive, is more expensive than to compute addition or subtraction. So the idea in Karatsuba algorithm is what we need is this, is the coefficient of this polynomial. So what we can do is to reduce the number of multiplication. So we are going to compute this product, and this product, which involves some summation and which involve addition. But since addition are cheap, it is not. It doesn't matter. But from these 3 products, we can compute this coefficient which we need. Since this product compute 2 products and compute addition is the product are more expensive. So we know this product, we know this product, and we know also this. What we want just to do is to do the subtraction. This is the idea in the Karatsuba algorithm. So we compute the coefficient of this polynomial by reducing the number of products since the products are cheap, expensive. Sorry. Now we have a result by Couvain and Lercier, and also with my former PhD student, Ramon Sal. So we consider G a one-dimensional connected algebraic group. We know that we have the classification. We have 3 affine and 1 projective, and 1 class of projective algebraic group. We consider a cyclic chopper of order n. We know that we have the quotient isogeny. We assume that the fiber above a k-rational point is reducible. This means that we have a cyclic. We saw that we have a cyclic extension. But we also have a divisor. The divisor will be constructed by the fiber. We also have a function. Remember that we saw that we have a function on elliptic curve. We saw also that we have a function on the locus torus. In the additive group and multiplicative group, it is easy. But if we have a point, a FQ rational point in the algebraic group, then we have a bijection between a linear space, some linear space, and this vector space. We assume that we have this rational point such that we have this bijection between the two vector space. If we have this condition, then for any B in the fiber outside of the absorption, we have a normal basis which has a good complexity for the multiplication. Remember that I explained what is the complexity. The complexity here is the running time, the number of operations needed to compute the product, the multiplication. So here are some idea for the proof. This to see that we already explained why this extension is cyclic with degree n. We explain why we have the function. They are linearly independent, and the evaluation gives us a normal basis. Remember that the function are constructed by using this translation, which is related to the Galois group. So it is normal basis. Now we want to compute. We want to see how to efficiently compute the. Sorry, I'm looking for the time. It remains. I think I have 5 or 10 minutes, so I have to finish. We have. So we want to do this project. We want to compute it efficiently. What we do is we have two elements in the top field expressed in using the normal basis. From the element we construct from the element A, we construct the function A. We construct from B the function B. We have this C, which you will understand in a few minutes why we have this C. And what we know is that if we can compute the evaluation of the function B, the evaluation of the function D at B, then we have, by adding D and C, we'll have the expression of the product A times B in the basis of what we want. Remember that the normal basis is the evaluation of the function U at B. So if we evaluate A, if we have we evaluate D at small b, and we have the expression of D of small b in the basis theta, and we have also the same thing for C. When we do C plus D, we have the expression, the linear combination giving us the coordinate of this product. That's what we do by using evaluation interpolation. We first evaluate D by using tensor product. In fact, remember that we have a point R such that we have a bijection between the linear space L1 and we have this bijection between the linear space L1 and this vector space. So, and here, this bijection, we know how to compute the inverse. The inverse in compute is computed by using convolution product. So, if we know how to evaluate, this means that we are in this vector space. To come back in the linear space, we use the convolution product, but this will give us what we want. I mean, the expression of the product in the normal basis. That's what we do. So we do evaluation and interpolation. This is the fast Fourier transform this is a fast Fourier transform like algorithm. We use the same idea. So at the end, when we have all evaluation, we have the coordinate, then we come back, and when we come back, we have the expression what we want. But so when we are looking for the running time, we see that the convolution product is the more expensive part of the algorithm. But we have there are many, not many, but yes, we can find how to compute efficiently convolution product in many books. So and we know that the running time is quasi-linear. So the proof is complete. Now, when we are doing finite field arithmetic, we have some ideas. The first one is we have a finite field extension for which we have an efficient normal basis, but we do not usually have an efficient normal basis. It can be that for some there are some finite field extension for which there are not efficient normal basis. The normal basis theorem says that every Galois extension has a normal basis, but we do not know if the normal basis is efficient or not. When I say efficient, I mean that we can compute efficiently multiplication. So if we have an extension where the normal basis is not efficient, what we do is to factorize the degree of the extension. And we are looking for a factor of the degree for which we will have a normal basis, and then we are going to extend the basis. If we found a divisor of the degree, and such that the corresponding intermediate field has a normal basis, then we can extend this basis, and using the ideas from Karatsuba algorithm and so on, we can also get an efficient finite field arithmetic. And the first paper explaining this kind of thing was written by Thomson and Bayer in 2018, and they use Artin-Schreier theory. Since Artin-Schreier-Witt theory extend Artin-Schreier theory, we use Artin-Schreier-Witt theory with my former PhD student Sal to complete the work by Thomson and Bayer. And we also use Kummer theory. And here, the result is that when you use Kummer theory, you get better result because we can see that Kummer polynomials are sparser than Artin-Schreier polynomial. So that's what I was wanting to explain to you. I thank you for your attention.